Exam 3. Pull up the thing. That look good. Sweet. Are you guys ready for exam 3? Okay, well, if you're not, it's okay. No one ever is. That's how exams work. Okay, let's get started. So exam 3 opens tomorrow and it closes on Monday. Monday, the testing center closes at like 6 or 7 or something. I think doors close at 6, so just be aware. You can't wait till like 8 to go take it because then you've already missed it. There's going to be a 3-hour time limit, so kind of on a time crunch, but not really. It's just like the other ones you've done before. There's going to be 20 multiple choice questions and 5 free response questions, so really not that much. You got it. Any questions about logistics or anything? Okie dokie. This slide is just there to say you've got lots of study materials. I personally like the exam 3 study guide a lot. Goes over what you need to know. She puts those together after she's made the exams. So she's just like, oh, this and this is gonna be on the exam. You could look at these other things too. All of those are helpful. Class slides, your notes if you take notes. Wait, let's get started with gas laws. Give me a good review. So first thing we need to talk about is kinetic molecular theory. And this sounds like a lot up on the board, and there is. I mean, there's a lot of words up there. But basically, what you need to know is kinetic molecular theory is just a model that we have. These 5 things are just like rules that we have to understand gases and how they behave. Okay, so I personally wouldn't memorize these word for word, but I would know the general idea and be able to list them without looking at this slide. So that when free response questions come up or multiple choice questions come up asking about this, or asking about the behavior of gas, you're going to be able to know this. So, I mean, you can read, right? It's pretty self-explanatory. And most of this we've repeated lots of times. Does anyone have questions about kinetic molecular theory? Yeah.
Just to like use it to prove something.
Mm-hmm.
How exact on wording?
As long as you get the general idea, we really try to fight to give you guys points. So as long as you can get the gist, you're not going to have to write word for word what it is. But if you can get the basic idea, then we'll give you points. Okay, that is super important to know. Know it, don't memorize it. If you want to memorize it, you can, but that's weird. Let's talk about effusion and diffusion. So these things are pretty much the same. Someone in my recitation today said that diffusion is just a fusion with a really big hole, which I mean, I guess it's true. But effusion and diffusion are just gases moving, right? So diffusion is when you have a gas and it just moves through space. Like when you're sitting in lecture and someone opens up this thing of really gross, like seafood, tuna, something, and you're sitting like right next to them. You can't move. The smell, it diffuses over to you. It stays there for the whole lecture. It's awful. The other thing is effusion. It's when you have a tiny hole and all the gas escapes. It's like when you poke a little hole in the balloon, it doesn't pop, but you have a little hole and the gas slowly leaks out. That is effusion. Any questions about what those are? Pretty simple stuff. Okay, let's make it not simple. So we have Graham's law. Graham's law is basically the law that you need to know for effusion and diffusion. With Graham's law, you can calculate root mean square speed, okay? Which you're gonna need to do, and we're gonna do some practice problems with it. And you can also compare rates of effusion and diffusion, okay? Any questions about these formulas? Yeah.
In molecular weight or
it is molar mass, so yes. Yeah.
Which R is it?
Which R?
Is it the 8?
Oh, this is the 8.314 joules per mole Kelvin. So you have to know when to use which R. Yeah.
What's that symbol on the first one that's between the two?
That means proportional to.
Okay.
So the root mean square speed is proportional to 1 over the square root of molar mass, which is why we can do this other equation. So great question. Any other questions?
Do we need to know the proportional thing, or?
I mean, as long as you know those two things, the root mean squared equation and this one, we're not gonna ask you. I mean, maybe they'll ask you. Sure, know it. Why not? But they're on your equation sheet, so I wouldn't worry about it too much. Okay, any other questions? Okay, let us do some practice problems. Okay, so this is the equations down below. Guys, today we're going to be doing lots of practice problems, so I would get out a spare piece of paper, your pencil to write, obviously, calculator, equation sheet. We're going to do lots of practice problems. So I'll give you a minute for that. But while you're getting ready, those of you who are ready can start. This is the first practice problem. Ready, set, go. And if you have any questions while we're doing it, I can turn off my mic. Just raise your hand and I'll come over. I'm going to give you guys like one more minute.
Even though it said custom California, so that part easy. So. Yeah. It is a joule, baby. Meters per second, son.
Figure it out. Science.
It's the same one I use. It's easy to use.
That's great.
Okay, you guys ready for the answer? No, someone's saying no. Yeah, I'll give you guys like 30 more seconds.
You can have one. Too many. So still try to get him.
Here's a hard.
Got a shot. I can this.
Okay, guys, here is the answer. Ready?
But yeah.
Who got that answer? Good job. It's okay if you didn't. We're gonna go through it right now, and actually I went through it already. So there is my work.
Yeah.
Oh, we did.
So can anyone tell me why we need the molar mass in kilograms per mole? Yeah, the R is in kilograms, right? So when we're using this 8.314, we always have to look at units when we're doing equations, guys. So this 8.314 is joules per Kelvin times moles, okay? And what is a joule? A joule is kilograms times meters squared over seconds squared. Oh, kilograms. Okay, so if we use grams per mole for the molar mass on the bottom, this kilograms doesn't cancel out. So we have to use kilograms per mole. Here, I'll do the equation, but it'll just be the units, okay? So 3 doesn't have any units, and then we have this kilograms, meters squared, seconds squared. And we have Kelvin. And we have Kelvin. Oh, wait, no. Messed that up. Sorry. Let me try again. So we have the joules, right? Which we know is kilograms, meters squared, seconds squared, and it's over Kelvin times mole. Then we have the Kelvin right here. And then we have, we're going to do kilograms per mole, right? So with this, if we have all the right units and we convert everything to the right units, these kilograms cancel. These kelvins cancel. These moles cancel. And we're left with meters squared per second squared. We do a square root. We're left with meters per second, which is always what it's going to be. So always make sure your units are right. They're a helpful guideline for if you don't know what you need to convert your stuff to. Questions about that? Yeah.
Square is just kind of like the average velocity.
Yeah, it's the average velocity. It's a little different than average, but it's essentially the same. Okay, let's do another practice problem. Ready, set, go.
Another one. And then it's effectively average.
Okay, guys, like 30 more seconds.
Because a for where it's nitrogen. Nitrogen gases. Two. That's a limitary substance. That's what I got here.
Okay, who's ready for the answer?
I
Okay, here it is. Is that what you guys got?
let's go.
Hey, there we go. For those of you who didn't get it, that's okay. Here's the work. So it's just a little bit of algebra, and you have to know where to put the 4.20 and the 1. So when we say that the unknown is 4.2 times slower than nitrogen gas, we can just put the 4.2 for the rate of the nitrogen gas. And then the other one is just 1, right? That makes sense? Okay. Any questions about this problem? Yeah.
We still polyatomic ions.
You should still know the polyatomic ions. Yeah.
You apply
I don't know if you're gonna need, you're probably not gonna be tested on them, but there are gonna be, there's gonna be problems that's gonna say, this is the carbonate ion. Or like you have the carbonate ion and it has a rate of effusion of this, you know what I mean? So, still know those ions. Any other questions? Great question. Awesome. Okay. Next slide. Okay, let's talk about temperature, kinetic energy, and molecular speeds. We were just talking about root mean square speed. We have the formula up there again. But we need to know these three things because temperature does affect the speed of a molecule a ton. So the first thing is that no matter what the substance, or I guess, no, wait. Right, okay, yeah, that's true. So no matter what the substance, everything at the same temperature has the same average kinetic energy. Okay, they might not have the same root mean square speed. Slower things have lower root mean square speeds. But at the same temperature, they all have the same kinetic energy, right? Because the formula for kinetic energy has mass in there, right? Okay, so it's all the same kinetic energy, temperature, kinetic energy, they go together. The higher the temperature, the higher the kinetic energy, okay? That doesn't mean that velocity is the same. The root mean square speed changes between masses. The heavier masses have lower root mean square speed. Kinetic energy is the same, okay? Next thing, I think I just said that second one. And as temperature goes up, kinetic energy increases. So average speed also increases. Oh, I said that one too. Okay, any other questions? Sorry, just any questions? Who has questions? I've got questions. Okay, no questions? Awesome. Let's move on. Talk about the combined gas law. So the ideal gas law and the combined gas law, they are functionally the same. But there are going to be problems on the exam where we're going to do a practice problem real quick that uses the combined gas law. But where it gives you like two values, maybe pressure and temperature, and you have to use the combined gas law to figure out, and it'll give you two original ones. Like the pressure was this, the temperature was this. If we raise the temperature to this, what is the pressure of this one? Right? Pretty simple. I just tried to grab chalk and there's no chalk. So for that one, I think it would be something like P over T equal P1 over T1 equals P2 over T2, right? But that's what it would simplify to. But basically, we know that P times pressure times volume over number of moles times temperature is always going to be equal to this gas constant R, right? It's always going to be equal to 0.08250557. I don't know what it is. Okay. It's always going to be equal to that. So because it's always equal to this constant, if we have one gas, we can have another gas. They're both going to be equal to this. Okay. So we can do like comparisons, math problems. Just take out of this equation what stays the same. So in my example, the number of moles stayed the same and the volume stayed the same. So we would just do P over T. Does that make sense? Again, it's pretty simple. We're gonna do a practice problem just to practice. It's kind of, oh, this is good. Okay, go through, talk with your people around you, how these variables would change as we change other stuff. Okay, ready, set, go.
Doing all this. So it's like increasing because temperature. Oh, I don't think just like that. Like what happened? Yeah, it like takes away. Sure goes up. First, you return for temperature.
Okay, shout it out to me. What would happen on the first one? How would the volume change? Half. Yeah, it'd be half. Does that make sense? Okay. What about the second one? How would the amount of moles change? It wouldn't change. Okay. How about the temperature? Also wouldn't change. Okay, what about the last one? What happens to the temperature? If we return the pressure back to normal, but then we added double the moles, what happens then? Temperature is half as much, right? Does that make sense how we're doing that? Yes, I think.
Why doesn't temperature change if we double pressure?
Because this is our equation right here, PV over NT equals R. So if we change, N is gonna be 5, T is gonna be also 5. Let's just make everything 5. 5 is a good number. Pressure of 5, volume of 5 equals 5 times 5 over, okay, but it doesn't matter, the math, whatever. If we add, it's going to equal, this equation is always going to equal this number. Right? It's a constant, so it's not going to change. So if we double this and change this 5 to a 10, that wouldn't be the same thing anymore. That'd be 2R. So we have to half this, right? So that would be 2.5. The other things don't change. Because if we change the other things, then it would change the R. Yeah.
So if you keep volume the same, then temperature would change.
Wait, what'd you say?
If you keep volume the same, temperature would change.
That's true. But yeah. I guess it would. All right, whatever. Doesn't matter. Let's do a practice problem. You broke my practice problem, Isaac. Okay, here's a practice problem. Ready, set, go.
Sometimes.
What is this like? What does this have to do with?
Canister of compressed air in mine. I don't think I.
You need the.
A canister of compressed air.
I feel like
Perhaps this had more updates tonight.
there's no aluminum in Chem.
Definitely thought it would have like. Okay.
It's gotta explode.
So it's just what.
The temperature's going.
Compressed air from the coolant air. That was a sure, that was a rupture. I'm gonna do the math because from practice, that makes sense.
73.
Twice as many bullets. How does it not? Pressure doubles.
Is there football game tomorrow?
Pressure rate. Let's see, you've got.
You remember?
Max law or whatever.
Party.
It's P over T. It's P over T.
No, dude.
4.5. This makes me feel so confident. Our Kelvin. 7. Now we know. 2 months. 7.5. I don't think. Can you multiply that by? Oh, how much?
Do sure. Atmosphere 873 divided by
So
7.
this pressure.
73. 3.7 means the
Atmosphere is
okay. So like the equation looks like EV over R equals MT.
All right.
How much?
Okay, who's ready for the answer? Are we ready?
Oh,
No? Okay. Feisty nose in there.
you know. How much?
Maybe 2. So I feel like it's gonna be.
Just all you do. Where's this?
You name my head. Question. Where did that erase a star marker on the telephone board.
Okay, I'm gonna show you the answer. Ready or not? There's the answer. So even though, so someone told me that we only have one sig fig on the pressure, and that's true. So don't worry about the sig figs on this question. I didn't write it. I did write the first part. I thought that was funny. But don't worry about that for this one. On the test, it's going to be better with like sig figs and the right number of numbers. But the answer is yes. Did you guys understand how we did that problem? Okay, awesome. Okay, let's talk about the ideal gas law. So this is the same thing that we were just doing, right? Pressure times volume equals number of moles times the gas constant times temperature. Okay, you should always use those units, always convert to those units when you're doing ideal gas law. And you should understand that the ideal gas law makes two assumptions, in that there is no intermolecular forces between the molecules, and the molecules don't take up space. Those aren't true, because obviously there are intermolecular forces, and things do take up space. So it's not like super concrete, but it's an estimation, and it's easier than the other one. Questions about the ideal gas law? Solid. STP, okay. You guys are going to get into the test. You're going to be like, you studied all the really complicated stuff. I don't know if there's a ton of complicated stuff, but there might be. And you're going to forget the small things. That's what happens. So just remember that at STP, standard temperature and pressure, the standard temperature is 273.15 Kelvin.
I'm sorry, not like 0 degrees Celsius.
You're right. That is not, it should be 298. Shouldn't it be 25 degrees Celsius? What is the temperature?
273.15.
And the temperature is 25 degrees Celsius.
The standard.
No, standard temperature is not freezing. I did this slide wrong.
No. What?
No, what? You told us it was 270.
That's right.
This is right.
Right.
It is right.
The temperature is defined as 0 degrees Celsius.
Yeah.
Okay, there we go. You guys made me doubt myself. Gotta cut you toxic people out of my life. Just kidding, just kidding.
So I've done too much, Alex, for this.
Oh, dang it.
Do that. Oh.
All right, let's start at the beginning again.
It's a very good place to start. Maybe. I'm not the one who started whistling it.
Okay. Okay, so this is it. This is right. 1 atmosphere, and the volume is 22.4 liters. Okay, memorize that stuff. It's not on your equation sheet. You just have to know it. There are going to be problems that says, imagine this reaction happens, or that this is at STP. Find the blank blank. I don't know. So you should know what STP is. These 3 values. Okay. Questions? Yeah.
The reason that you can say molar volume of any gas is that specific number is because of the ideal gas law, right?
Yeah.
And if we're talking real gas, that wouldn't.
Yes. Right. If we're talking real gas, it's not that, but this works for us. Okay. So this is STP. Know these values. Any other questions? Great question. Yeah.
What is the ideal gas law like more real? Wouldn't that like increase temperature or something?
Sorry, what?
Like the ideal gas law, like there is a point where like intermolecular pollution, and so it's like more.
Yes, and we're going to talk about that real soon. So, yes. I think it's at low temperature and high pressure. That is when it doesn't work. Because at low temperature, the intermolecular forces affect it more because they have more time to do it, as opposed to high temperature where they're moving around. This is the molecules, right? And at high pressure, the volume of the molecules has a bigger impact on besides low pressure, right? Great question. Okay, so something you should be able to do is find the molar mass of an unknown using the gas law. So this is how you can derive this equation from PV equals nRT. I didn't do that because that's a lot of extra math. I just memorized that. So you could do that if you want. You can memorize it. You can understand how to derive it. Does this derivation make sense?
Yes.
Yes. Yeah.
Small m is the.
Small m is mass.
Mass of.
So you're going to be given, you have like 42 grams of a substance. That's where you put the 42 grams in. It's the mass of your thing. The big M is the molar mass. Okay. Any questions about the formula? Yeah. 0.0. Yeah, it is. The only time you're going to be using the other one is in the root mean squared equation. Okay. Practice equation or problem. Ready to go.
It should be there, but you might have.
Yeah, no. Grams aren't.
Going off.
Grams are, they are mass.
Right. Did you write this problem?
I did, I had fun with it.
That last sentence is.
I was really, but their unit of mass.
So what happened is I spent like 5 hours making a review, and then I was doing the second to last slide, corrupted. I lost it all, so I had to do it again. So this second time, I was like, you know what? I had fun with it.
Wild guess.
That's good. This is a good practice problem. Validate.
Yes.
Fabulous.
Thank you.
Perhaps the best.
Names. Names.
What is the molar mass, this wild gas, and it's the nocton here.
Literally has it like, and we don't even have to.
That's how it is.
Does anyone need more time? Okay, 30 more seconds.
I got the same thing.
That knocked you on your, what is the molar mass of this fucking mass at the top? Nice. Oh. Hydrogen gas. Was knocked over by hydrogen gas. That's embarrassing. Maybe that's not embarrassing.
It's a lot.
Yeah, I think
it's 600.
Yeah.
Possible is. Was I knocked over by gas? Was I not?
Okay, let's show you the answer. Ready? No? Okay, I'm gonna show you the answer anyway. Okay. Did people get this answer? Yes. Okay, solid. Does it make sense? Probably not. For the molar mass of this gas. Kind of weird. Really light, but whatever. You guys did the math. Solid. Okay. Questions about how we did the problem? No? Any brave soul want to come up and do the problem on the board? 3 brave souls, all of you. Let's go. Race to finish it, all 3 of you. Unless you don't want to do that. Okay, ready? Wait, we can't start yet. Don't start. Ready, set, go. Let's put money on it. Don't throw. While they're working on it, did anyone have any questions? No questions? Yeah.
If you were to predict the identity of the gas, what would you say that it was?
If I was to predict the identity of the gas, Probably, let's see. I don't know if there is a gas that matches this. Probably hydrogen is the closest thing that it could be. But I don't think hydrogen is 2.16, is it? I don't think so.
Well, but it's
2.016, I think it is. Yeah, I don't know. I just came up with these numbers randomly. So. Oh, snap. Good job, Jacob.
Almost done.
Keep going. Good job. Second place is good too. Okay. Sweet. There's no other questions? Go on. Okay, the other thing that you need to do is density, and it's pretty similar to the other thing we just did. I know you guys are probably sick of them, but we have a practice problem. So this one is pretty simple. So I'm only gonna give you guys like a minute. So ready, set, go.
The grams. Your way. X 6. Oh. Divided by R. 2. 8. And fluoride is way. Says. Here. Over hexafluoride. I was about to. And my temperature so hard now. I'd have to try and like memorize it right, but then type it in.
Okay, you guys ready? You guys get that? Nice. So you should know how to be able to do these two things, molar mass and density. There are going to be questions about this. So good luck. Practice it, memorize it. Okay. Yeah.
We're not going to be given the derived equation, sorry.
No, you're not going to be given these derived equations. Okay. So you're not going to be given this and you're not going to be given that.
Yes, we are. It's on our equation sheet.
Oh, it is?
Yeah.
Oh, I didn't have it. You guys are lucky.
I mean, it's still, it's mass. I mean,
You guys are soft. New generation. Weak.
so.
Back in my day. Okay, let's talk about mole fractions. There was no equation sheet. We had to write our own equation sheet. That's not true. There was. Okay, mole fractions. What do we need to know about mole fractions? So we need to know that pressure, first of all, the total pressure is the sum of all the partial pressure. So if you have a mix of gases, each of those gases has their own partial pressure that they're contributing. Okay, it's like teamwork. Weird. Okay, not that teamwork is weird. Never mind. So obviously total moles is the sum of all the moles. Okay, that one's pretty intuitive. Identity doesn't matter, which is pretty important to know. Okay, so these are the two equations you should know, and apparently your equation sheet has all the answers on it. So does your equation sheet have these on it? No? Wow. Which you guys have to memorize. So I would memorize these two because they're pretty important. You're going to be given questions that deal with partial pressures. So you should be able to find the mole fraction, which is this first equation. And you should be able to find the partial pressure, which is this other equation. Okay? And obviously you can manipulate the variables to find out different things if different things are missing. Yeah.
Yeah, identity doesn't matter. Plugging things. What do you think?
So for neither of these things do identity matter. So identity of the substance, say it was CO2 versus H2, it's not going to affect the partial pressure. Yeah.
So X1, that's mole fraction, right?
Yeah. X1 is the mole fraction of gas 1. So we could pretend we have like gas 1, gas 2, gas 3. X1 would be the mole fraction of gas 1. Yeah.
You need to know the name of the laws.
I'm not sure on that one. What do you mean, laws?
It's like Gressel law.
I would know the names. I would know the names. Yeah. So know the names of those. Yeah. Okay. Sweet. Let's move on. Oh my gosh, another practice problem. Wow. Okay, ready, set, go.
I'm using nitrogen. Gasoline. Okay, let's ask you for nitrogen, you're asking for mole fraction. Nitrogen is not diatomic, that's true. But after this. I can't. Nine. Mole fraction. And 2, it's gotta be. I guess it's. 7. Really? No. I tried. We have another break if you want to ditch us again. 9. This really cool. If you want to go color height divided by ground squares. Well, 16 divided by, that's one where I do. That's the most.
Okay. Everyone's done with this one. This is a bit of a shorter question. Guys, whose fingers hurt from doing the calculator? Sometimes my brain hurts, too much math. And like for some reason my fingers hurt even though I'm just pressing buttons. Ugh. Okay. That is the answer. Did we get this answer? No? What? Yeah, I didn't write this question. Someone come up, or just someone, what was the answer you got? Yeah. A third? 1/2? Oh no. Oh, dang it. Guys, did you use N2?
Well, all of those are. Aren't into those. So helium isn't diatomic. You have 2 moles of helium.
Yes. So helium is not diatomic. Helium is just He, whereas oxygen is O2, nitrogen is N2, helium is half. It should be 1/2. Is that the right answer?
0.25. It'd be 0.25. It'd be a quarter. 0.25.
All right, guys, let's do this question. I want.
Or okay, so there's half a mole of oxygen gas, half of a.
First, I want everyone who doesn't think it's 0.5 to raise their hand so I know to laugh at.
Is it 1/4? Okay. 0.25. I didn't write this question. I blame other people. I'm spotless. Just kidding. What?
So the question.
We should still do the question? Okay, that's a good idea. Let's do the question. Oh, what happened? Chip. So what do we need to do first? Someone shout out what we need to do first.
Yeah, change all the moles.
We need to find the number of total moles, right? So we need to do some conversions. So how many moles are in O2? What's the molar mass of O2?
32.
32, 30, close enough to 32. we'll say 32. Don't do that on the exam. Use the actual decimal spots. Okay, it'd be like 31.0, I don't know what it is.
Literally.
2,000.
But there's 32 grams of O2 for 1 mole of O2. Someone do the math. What does that equal? Okay, 1/2. Good enough. Let's do the same thing for our 14 grams of N2. There's pretty much 28 grams of N2 for 1 mole of N2. How many is that? 1/2. And with the last thing we have is 4 grams of helium. Sorry, I can't see, I'm in the way. And there's 2 grams of helium per 1 mole.
They're like a super.
Oh, there's 4. You're right.
Gotcha.
How many moles? This is easy. 1. So how many total moles do we have?
2.
2 total moles. What are we looking for? We're looking for the mole fraction of nitrogen. 1/2 over 2 equals 1/4. Okay. So it was 0.25. My bad. Okay. I'll fix that later. I'll fix it out when I put it online. Okay. Any questions now that we've done that? Oh, sorry. Yes. Is there a question over there? Is there not a question over there? Question.
When we're given pressures on this, is it in atmospheres?
Yes, probably. I mean, it'll have units for it. Yeah, it'll have units for it. It doesn't give us. It doesn't give us.
With pressure too, right?
Right. You can do it with pressure also. Okay. Yeah.
Ideal gas level, salt, pressure, and then able to solve for pressure using that.
Yeah. Yeah, totally. I think it'd be harder, but I think you could.
Would the moles be like just the moles is 2?
Yes.
And then you,
But I mean, it depends on what you're solving for. But yeah. If you're trying to find the total pressure, yeah, then yeah, you could do it. Yeah. That was a great question. Thank you. Any other questions? Okay, we're almost done with gas laws. Almost done. Let's talk about the solubility of gases, right? Solubility of gases just means the ability for the gas to go into liquid, right? And how well it does that. So solubility of gases, if you increase the partial pressure of a gas above a liquid, it will increase the solubility of that gas in the liquid, which is basically just saying if we have a liquid, we have a really high pressure gas above that liquid, it's going to go into the liquid. That makes sense? It's going to squeeze down in there, which sounds okay. Does that make sense? We can use Henry's law for this, which is just C equals K times P, P being the partial pressure of that gas, K being Henry's law constant. I don't think you're going to have to do any Henry's law questions, but if you do, then C is the concentration of the gas moles per liter. I actually don't think you're going to have to do any of these. Did you do any of these Henry's law questions on Alex?
On Alex, yeah.
On Alex, yeah. On your recitation problem sets? Yeah. Okay. So I know how to do this. Any questions about Henry's law? Yeah.
Is that constant given in a lot of situations?
That constant's always given, unless you have to solve for it.
Okay.
Unless it's the only thing that's not given. Okay. The other thing we should know is that the solubility of a gas decreases when we increase the temperature of the liquid, which makes sense, right? Because that's why we're boiling water. Water leaves, or the gas leaves. Okay. Does that make sense? The opposite is true for solids, like salt. Salt dissolves better in hot water than cold water. Yeah. Questions? Yeah.
the temperature of the gas.
Then some of the kinetic energy from the gas molecules will go into the water, and then it'll be more soluble. Does that make sense? So if you increase the gas, it'll also be more soluble. Oh, wait.
And the opposite.
I think it's the opposite of what I just said. Yeah, It's the opposite of what I just said. Sorry, I got it messed up in my head. Because if you have a hot gas, it's going to heat up the water, not very much, but it's going to heat up the water. And as temperature increases, the solubility of a gas decreases. So it'll decrease the solubility. Okay, sorry, that was confusing. I got it mixed up in my head. Thanks to whoever corrected me. Any questions? Okay. Talk about real gases. So someone brought this up, and we talked about this a little bit, but we talked about how the ideal gas law just makes some assumptions of reality that aren't true, that intermolecular forces between the gas molecules don't exist. They do, and that the molecules of the gas don't take up space. They do. So we have to correct for that, which is why you have that funky looking equation on your equation sheet. It's called the van der Waals equation. So at low temperature and high pressure, these gases deviate the most from ideal gas law, okay? So we have an equation to account for those. At the bottom, first of all, this is if you have a problem, it'll look like this, okay? It'll give you the constants A and B. So it's pretty much just a plug and check, okay? But first we have the P, and then we have the V. And in the P, we're correcting for molecular attraction, the intermolecular forces, because as intermolecular forces decrease pressure, right? Because as the molecules, let's say we have two molecules going in straight lines, they're passing next to each other. The intermolecular forces are kind of going to slow them down a little bit. So it's going to be less pressure, okay? So we have in the P part of the equation, we're adding a little bit to account for that, yeah.
Sorry, when you say like it's gonna be a plug and chug, is the whole equation gonna be given or just the A and B?
Is your equation on the, yeah, so, yeah. For the other part, volume, molecules take up volume. So we have to subtract the volume of the molecules, which is what we're going to be doing there. It's the number of moles times B, and you'll be given B, okay? Does this make sense? It's pretty much just look at the variables and plug it into your calculator, okay? But you should be able to distinguish A and B and know why they're there. Okay, so A is correcting for the intermolecular forces of the molecules. B is correcting for the volume of the molecule. Okay, yeah.
And this equation, yeah, it's the ideal gas law varies more when it's what? High temperature? Low temperature.
It's low temperature, high pressure. Low temperature is when intermolecular forces act on the molecules the most, right? Because the molecules have a lower average kinetic energy. They're slower, so they pass by each other slower. That gives more time for the intermolecular forces to act on them. At high pressure, it's really squeezed down there. There's not a ton of volume between the molecules. But our assumption that the gases, the molecules of the gas don't take up any volume is especially not true there. It's not true everywhere, but especially not true there when it's super, super, super compressed, right? Because that volume, it's not as big as we think because the molecules are actually taking up a little bit of that volume, okay? Okay. So onward. Okay, this is a break. So if you want to take like a 5-minute break, get some water, you can. I think it's very funny. So yeah, take a break if you want.
Like they, that's never answering, which is so bad.
Oh, from Boston. Except the ideal gas law.
They,
Oh, yeah. What was the?
Till like 7:30.
How you doing? Pretty good. Trying to watch to the cycle, man. Application are due in like months. I think they could be open. I got my last letter of recommendation. Just say no. I need to preempt it because Michael will do. It's already written, and then I have a doctor. That's the thing. I'm a doctor. I don't know.
Okay, guys, is that 5 minutes? Is that close enough? No?
I just want to get them.
Do we want to keep going anyways? Yeah, okay. Let's try to get this done. Okay. Okay. That was a funny meme. Let's keep going. We're going to shift. We were talking about gas laws. Now we're going to be talking about intermolecular forces. Okay, let's get into it. So first we have, earlier in the semester, we were talking a lot about intramolecular forces, which is like covalent bonds and metallic bonds. And we talked about ionic bonds being a intramolecular force. But right now we're going to be talking about intermolecular forces. Guys, thanks. So intermolecular forces are forces between molecules. So you have two separate molecules. Each molecule has their own intramolecular forces, like covalent bonds and stuff. And then you have forces acting on those two molecules, like on the dispersion forces or dipole-dipole or anything like that. Okay. So the reason we care about intermolecular forces and we talk about it so much is because it has a lot to do and it dictates the physical properties of those substances. Okay. So when we're talking about intermolecular forces, try to think of it through Coulomb's law. Okay. You should be able to describe all of these intermolecular forces and why one is weaker than the other or stronger than the other through Coulomb's law, which we're going to do. Okay. So let's get into London dispersion forces. London dispersion forces, everything has London dispersion forces. And they're dictated by something called polarizability. Okay. So let's go up on the board. And I'm going to draw a simple molecule. Let's just do like, I don't know, Cl2, some good old chlorine gas. Okay. So these dots, let's assume they're chlorine atoms. Okay. We know from past semesters that these atoms have electron clouds, right? And it's probably not going to look like that. I mean, that was a pretty not great drawing. But on chlorine atoms, especially, they have a very big electron cloud, right? Their N is really big, their shell, and it's pretty close over there. So pretty big electron cloud. The bigger the electron cloud, the more polarizable it is. And polarizability is just the ability of the electron cloud to move around and create temporary or permanent or temporary dipoles. Okay, so right here, I've drawn it. So this has a little bit less of the electrons. So it's kind of positive, right? It's partially positive. This one's partially negative. It's just like what looks up there. Okay. So these are temporary. They don't last for long. It kind of shifts around. But all molecules do this. That's why they're temporary. That's why everything has London dispersion forces. Okay. Yeah.
We're talking about bigger. Are we talking about the atomic radius or the atomic mass?
The atomic radius. Okay. Which is what we talked about last semester with like, as you go down, N increases. So you have bigger electron clouds. And as you go over, I think it was, I can't remember, but as you go over, it gets smaller.
So something like it's going to have bigger force than
Bromine is more polarizable than chlorine. Yeah. And iodine is even more polarizable than that. Okay. Yeah.
That London increased with.
I don't think it's with greater mass. Well, I guess I suppose so. It depends on what you're talking about. If you're talking about two different atoms, then no. But if you're talking about different molecules like this, as opposed to this, then yes, right? And this one's obviously going to have a higher molar mass. Okay, great question. Did that answer it? Okay. Yes.
Just want to make sure, isn't it, it's about surface area, and it's just that surface area is typically associated with greater mass?
When you have a big molecule, yeah, it's surface area. But when you're doing with diatomic things, it is the radius of the atoms
Bigger.
or the electron cloud. Yeah, the bigger it is, the more polarizable it is. So they're stronger and more frequent temporary dipoles. Yeah. Okay, solid. Any other questions about London dispersion forces? Yeah. Do you have a question? No? Oh, I thought you raised your hand. My bad. Okay, awesome. I like the thing at the bottom. Because everything is London dispersion forces always. So yes. Okay, dipole-dipole interactions. These are just molecules that have permanent dipoles. So polar bonds, they're attracted to each other, right? They're magnets. Okay. This one's not that, it's not super hard. It's pretty intuitive. Okay. Any questions about that one? Okay. Next thing we have is hydrogen bonding. So hydrogen bonding is just dipole-dipole interactions, but it's specific dipole-dipole interactions between an H that's bonded to an F, N, or O when it interacts with another F, N, or O. Okay. And it can only be those three. Other ones, those are still dipole-dipole, right? If both molecules are polar, they're just not hydrogen bond. This is because of the small size and high electronegativity of N, O, and F, right? Coulomb's law, which I'm going to write Coulomb's law up on the board just so that we have it. So charge 1 times charge 2 over the distance between the two things. Okay. And because N, O, and F are really, really small, but they have big electronegativity, they end up having more polar bonds. So the force is bigger. Okay. Any questions about? Yeah.
Like, I think it was on one of the practice problems, but we had like a long chain that ended with an alcohol group.
Okay.
Right, and the question was asking about like the strength of the hydrogen bonding at that point. Could you, like, I think the longer the length, the weaker the hydrogen bonding. Could you kind of explain that or something?
Yeah, so hydrogen bonding is always strong, right? But there's a lot of steric hindrance, which is just saying that this long chain is getting in the way. So it can only hydrogen bond in this one spot. And let's say we have a bunch of these and we throw them into water. So there's a bunch of H2O and there's a bunch of these, okay? It's still gonna hydrogen bond right here with water. So you'd think it would be miscible, right? Mixable. But because these are nonpolar right here, this part is gonna wanna stick with its friends, right? The other ones that look like this. Okay, so even though it can hydrogen bond, it's still not gonna be super miscible. Did that answer your question? Was that kind of like the?
Of course, it's like the London in that case plays a bigger role. I don't know. I think I did.
Yeah, awesome, good. Any other questions about hydrogen bonding? Oh my gosh, a question. That's a great question. Let's talk about it. So probably on the free response question, you're gonna have to be able to draw a hydrogen bond. Okay, and you should know how to do it just so that the evil TAs don't take away points from you. Okay. Oh, I guess that's kind of. So what you want to do is where there's a hydrogen bond, you draw a dotted line. Or a dashed line or just whatever. And then you want to draw a box around it. Oh, whoops. Okay, that was bad, guys. Don't do that. Go all the way around all three. That was wrong, guys. That's really embarrassing.
The other way.
It's the other way around. Okay. that this whole thing was wrong. Welcome. Okay. Is that better?
Yes.
Someone tell me, is that better?
Circle the oh.
Thank you. I know. I did it. Thank you. Thank you. I'm gonna be here all of like a little bit more. So this is how you draw a hydrogen bond. Don't do it the first way, that was just wrong. So you want to draw a box around the 3 atoms involved in the hydrogen bond. Draw the dashed line, indicating that there is interaction there. Should be good. Okay. Last intermolecular force that we have is ionic forces. This is just like salt, right? We've talked about these before. We know what they are. This is the strongest intermolecular force. It has about the same energy as covalent bonds. They are technically intermolecular forces because even though NaCl comes together, it's basically a package of 2 separate molecules, right? Because an ionic bond is when one atom gives electrons to the other atom. Okay, so they're basically like 2 molecules that are just really, really stuck together. So yeah. Okay, that makes sense. Awesome. This is the chart. I thought this was funny.
It's bigger.
You should be able to describe these in bond strength. The difference in bond strength between these with Coulomb's law for the test. Okay. Yes.
I thought covalent wasn't that strong.
Covalent is stronger than intermolecular force. Ionic is stronger than covalent. Okay. But yeah. Okay. So what we're gonna do is we're gonna go over. This is a little chart I drew. We're gonna go through Coulomb's law, and we're gonna describe these things. Okay. So starting with London dispersion. London dispersion is when we have 2 things that are both nonpolar, which means they have a very, very small charge. Okay. So even though they could have a really small distance between them, but because the charges of the things, they are temporary dipoles, so they do have a little bit of charge, right? But because they're so small, it's a very weak force. Of course, that compounds when you have a really big molecule. The force ends up getting stronger and stronger. But that makes sense, right? Using Coulomb's law. Yes.
What the London dispersion forces would be like if you had a really long carbon chain.
Polar temp. Like that. Yeah, totally. So this is a polar bond right here, right? So this has a partial negative charge. This has a partial positive charge, but everything else has a neutral charge. So even though this is a polar bond, the London dispersion forces on these one is still gonna act pretty strong. Does that answer your question, or was that not even close?
Stronger than any sort of dipole.
I think it's gonna depend. It'll depend a lot on the shape of the molecule. It's gonna be pretty clear on your exam. It's not gonna be like kind of iffy, could go either way. Yeah.
Like on that, what would you say the predominant?
That's real. I wouldn't know. I'd have to be given data. If it was something like this, I would say hydrogen bond. But on the other one, I wouldn't know what it was. So good question. Any other questions? Yes, sorry.
So when you're talking on there, the charges, are you talking about like that has like a positive charge or a negative charge? Or was the amount of valence electrons?
Positive, negative charge.
Okay, so
So London dispersion, the cloud moves. So sometimes there's a positive charge on the atoms, sometimes there's negative in the molecules. And so that when you have a ton of molecules, they're slightly attracted to each other because the cloud moves around, creates differing temporary charges. Next thing we have is dipole induced dipole, and this is, guys, this is the order of strength of the bonds. So we start out with ionic, then there's ion dipole, then there's hydrogen bonding, dipole, 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 induced dipole, and dispersion. Okay. And the reason is because Coulomb's law. Okay, if we have, let's go to dipole next. So when we have dipole, we have charges. Both of them have charges. They're not as strong as ionic charges, which is like a full charge. It's just a partial charge usually. And it's got a distance between it. So it's not as strong as an ionic bond. It's not as strong as a hydrogen bond, because hydrogen bonding are just dipole interactions, but really strong ones, really specific strong ones. So it is stronger than London dispersion because it has more of a charge, and that charge is permanent. Okay. Next thing is hydrogen bonding. We just talked about that. The N, the O, and the F, they are really, really electronegative. They also have this really small size. The size between the H and the O, N, or F is going to be pretty small. So it's going to have a stronger force than dipole. And we could say the same thing for the other things. Sorry, are there any questions? Yes.
So overall, if the distance between the like molecules is smaller, then it's overall stronger.
Yes. Right, because it's divided by the distance between the two things.
Thank you.
Okay, let's move on. We're almost done. So for each one of these compounds, go through with your groups and list what the predominant or the strongest intermolecular force would be if you have a lot of those things all together. Okay.
LDS, also LDS. First one, really strong one, unless is it polar, is it ionic?
Sorry, Na2O.
Fourth one. Oh, maybe it's like split.
Yeah.
That's gonna be.
Yeah.
Yeah.
Maybe what's through, just see,
So I know that's. Ionic.
Okay, right there is going to be
LDS again. Ionic, and then. Anything there?
That's pretty honest, not too.
Pretty good. Yeah. Saw it. Okay, what do you think the predominant molecular force for the first one would be? That is London dispersion. Smart. Yes, Carly. You're not going to be given another electronegativity table.
Have to have it.
Okay. You should just kind of know the trend. At least I haven't been told that you're going to be getting an electronegativity table.
get out.
Okay. What about the predominant intermolecular force for the second one? Dipole, the second one. Okay, that makes sense, right? Yeah. Yes. So when you're looking at a formula like this, you should be able to, a lot of the times it's going to be kind of in order of how it looks. And we used last semester, we learned, where am I going to draw? Over here. We learned molecular shape. Okay. So we have this O in the middle, and we have two CH3s. Right? And O wants two lone pairs, right? They have a neutral charge. It's got 6 things around it. No formal charge. So what is the hybridization of this molecule?
That makes sense.
sp3, right? It's sp3 because there's 4 groups around it. There's this bond, these lone pairs, and this bond. So sp3, there's 4 things around it. What is its shape? Bent, which means it's got polar bonds, right? Because the carbon and the oxygen, so it has a dipole. Okay. If you have a bunch of those, there's going to be a lot of dipole-dipole interactions going on. Yes. Draw the first one? Yes. So the first one, first thing we have is a CH3, so I'm just gonna do line notation. So ignore the thing in parentheses. So we have 3 C's that we see. So we could do 1, 2, 3, right? And the other one, that just needs this branching off. So it looks something like that, with hydrogen attached. Okay. What is the predominant intermolecular force for the next one? Next one. What about the next one? How about this next one? And this last one? Hydrogen bonding. So intelligent. Okay, guys. This one it can be tough to conceptualize. But I want you to do the same thing. Actually, let's just talk about it. How would stronger intermolecular forces affect boiling point? It raises the boiling point. Okay.
Polar dissolve.
What about for melting point? It raises the melting point. What about for enthalpy of vaporization?
Oh wait, a vaporization. That's
It raises it.
pretty.
Do you guys know what enthalpy of vaporization is?
I don't understand it, but it's basically the boiling point.
So enthalpy of vaporization is how much energy is required to put into a system to change the substance from a liquid phase to a gas phase. And the stronger the intermolecular forces, the stronger it's going to fight against changing. Okay, so the stronger the intermolecular forces, the higher the enthalpy of vaporization. Enthalpy of fusion, the next one, enthalpy of fusion, is how much energy you have to put into a system to change it from solid to liquid. And those both increase with increasing intermolecular forces. Okay, does that make sense? Did that explanation make sense? Sure, okay, good enough. How about for vapor pressure? Decreases it. Do we all know what vapor pressure is? No?
Not really.
So vapor pressure, I'm gonna use this cool light switch. Okay, so vapor pressure is the pressure of a vapor, imagine, above a liquid. Okay, so let's imagine we have this cup of water. We have H2O in here. I'm just gonna write a bunch of H2Os. Okay, let's put a lid on this cup. Okay, I'm not great at drawing, so just this is a lid. Okay, whatever. Got a lid on it. The vapor pressure is these molecules of water. They're going to be spontaneously leaving and turning into gas. Okay, they're also going to be coming back in and changing to a liquid. It's going to be bouncing around because what happens is at the top of this liquid, there's obviously going to be H2O molecules, and sometimes below them, an H2O molecule with a lot of kinetic energy will come up, smack them, and they leave into gas phase. They leave the liquid. Okay. So this vapor pressure is the pressure of the vapor of those molecules that have left the liquid above the liquid. So what would happen if we were to increase temperature? What do you think would happen? Would vapor pressure increase or decrease? It would increase. So as a temperature increases, vapor pressure also increases. And that makes sense, right? That's why we boil, well, that's not why we boil water. We boil water to get it hotter. But when we heat something up, there is more things that can condensate. What are they called? I don't know. Like if you have a bottle of water and you leave it out in the sun, there's going to be lots of condensation. So, because that means there's lots of vapor pressure, steam above the liquid. Whereas if you leave it in a cold day like today, it's not going to have a ton of condensation because the temperatures decrease, the vapors decrease, or the vapor pressures decrease. There's less vapor in that space. Okay. So stronger intermolecular forces decrease vapor pressure, right? And that makes sense because in order for there to be a vapor pressure, these molecules have to leave the liquid. And if you have stronger intermolecular forces, it's going to be harder to have the molecules leave out into the vapor. Okay, it's the same thing for volatility. Volatility is just how easy a liquid can change into the gas form, like what we're talking about, just spontaneously up and leave. When you have really, really weak intermolecular forces like what is it, ethane, which is literally just like I don't want to draw the other H's, but there's other H's. Okay. So when you have something with really weak intermolecular forces like ethane, it's a lot more volatile than something with water that can hydrogen bond. Okay, does that make sense? Because there's not a ton keeping it in the liquid. The molecules at the top of the liquid, if something comes up and smacks them, nothing's gonna fight it. It's just gonna go, okay, guess I'm out of here, losers. That's what it'll say, probably, I don't know. But that is volatility. Any questions on vapor pressure volatility? Yes.
This is a little off topic, but you talked about condensation.
Yep.
I guess my thought process would be like water bubbles with hot air molecules would
Yeah, miscibility.
lose temperature when they come in close.
That's the pen.
That's what would cause the phase change. But I guess I'm misunderstanding how you explained condensation.
So I guess don't worry about the condensation. Just know that as temperature increases, vapor pressure increases. Okay. Sorry, I didn't mean to be confusing with that, but yes.
Yeah.
Let's have the same imagery. We have one water bottle. It's like the plastic ones. It's mostly empty. So we have two of those exact same things. We put one in a hot environment in the sun or whatever. One in like a spooky empty basement where it's cold. I don't know why it's a basement, whatever. In the cold or in the hot one, if you squeeze the water bottle, it's gonna feel a lot more full. It's gonna be harder to squeeze. The other one, it's not gonna be as hard to squeeze because the vapor pressure is less. Okay. Did that kind of clear it up? Okay, awesome. Cool. So both of those decrease with increasing intermolecular forces. And I think those are the only two things that decrease the stronger the intermolecular forces get. Yeah.
Sorry, I'm a little confused. The vapor pressure. It's the
So they kind of go hand in hand. Great question. They kind of go hand in hand. Volatility is how easily they leave. Vapor pressure is just the pressure of the vapor above the liquid.
Okay.
So they're kind of like partners, but they are different. And those both decrease as you increase intermolecular forces. The next one is viscosity. We can all imagine viscosity increases as intermolecular forces increase, right? We know what viscosity is. Okay, the viscosity increases with increasing intermolecular forces. So does surface tension, and mixability, like Professor Sansom said, depends on what you're dissolving, right? So if you're trying to dissolve something non-polar into something polar, like ethanol into water, I guess that one would work. Let's talk about like wax or something. Okay, wax, super non-polar, super long carbon chain. It's longer than that, okay? It's not really gonna mix with water. They're gonna stay with their buddies where the intermolecular forces are stronger because of London dispersion. Water doesn't have a ton of London dispersion. That one doesn't have a ton of, well, it doesn't have anywhere to hydrogen bond, so they're not gonna mix. So polar mixes with polar, non-polar mixes with non-polar. Does that make sense? Okay. Any questions about any of these things? How increasing intermolecular forces changes them? Excellent. Okay, guys, this really is all reliable. On the free response, if she ever says anything about any of these things, just literally say that sentence because it's so true. And think about it too. You have to put more energy in to overcome intermolecular forces. Okay, so the stronger the intermolecular forces, the more energy you have to put in to overcome those forces. Okay. Okay, does that make sense? That was like the only useful meme I've had this whole presentation. Okay. Okay, we good with that? So water's kind of weird. You should just be able to describe these properties of water that we're going to go over. So let's go over density. Density, most things as they turn from liquid into solid they get more dense. Water gets less dense, right? Because when it's in the fluid, all the molecules are just jumbling around. But when they're in the liquid, they're all in hexagonally packed thingies like that. So it actually makes the space bigger. So water's just weird. So less dense when it's solid. Okay. Capillary action. You should know adhesion and cohesion. Pretty self-explanatory. Water, cohesions. I don't know. It's got a lot of cohesion with itself because the water molecules are very stuck to each other, right? So that's cohesion. And they also like to stick to other things. That's adhesion. So we have an example of something that is adhesive and cohesive and something that's not super adhesive. Does this make sense? Okay, getting lots of nods. Let's go on. Surface tension. We talked about surface tension. Water has a lot of surface tension because of the hydrogen bonds, super strong intermolecular forces, lots of surface tension. Okay. Heat capacity. You should know what heat capacity is. So water has a really high heat capacity. And basically, we're going to talk about a lot about this next semester. But heat capacity is just how much energy you have to put in to make it hotter. Right? So water has a really, really high heat capacity. And it's because hydrogen bonding, basically what it says up there, hydrogen bonding makes it funky. Basically, guys, if anyone says, why is water this way? The answer is hydrogen bonding. So I don't know, just throw that on there. It's also really good at solvating things like salt or other things because salt, NaCl, ionic bond, super, super strong. So when you put it in water, why does the bond break if it's such a strong bond? It's because water kind of attacks that with their magnety boy parts. Oh, that sounded weird. It just kind of interrupts the bonding and solvates it. Okay. Okay, last thing we're going to talk about, guys, we're almost done. Phase diagrams. So you should be able to, given a blank one of these, look at this and label all the parts. You should know where the triple point is. You should know where the critical point is when something's supercritical, like a supercritical fluid. You should know where solid goes, where liquid goes, where gas goes. Pretty, right? You should be able to label it. Yeah, is there a question? Yes. So it's at the end of this line. So yeah, it's where it turns into a supercritical fluid, which is really funky. Okay. Any questions about phase diagrams? Just know them, basically. Yeah. It melts or it freezes. The solid line just goes forever. The only one that ends is the gas and liquid line. That's where it turns supercritical. But the solid one goes forever. So it'll just, there's not really a top to the gas one. It's just the graph eventually has to end. Was there a question over there? Yeah. Yeah, one atmosphere. Yep. Okay, question? Yeah.
Just to be clear with the critical heat, it's everything above and you making the energy in space.
Yeah. Yep. Yeah. Okay. Huh. Yes, sorry, I'm sorry.
Can you help me understand what happens when you decrease the pressure when the temperature is low?
When you decrease the pressure and the temperature is low. So if we're going, let's get the Pikachu up. So if we're going decreasing pressure, so we're cutting this, temperature is low, it turns, because we're decreasing the pressure and the temperature is low, even though it's really low and it should be ice, when it's in a vacuum-like state, the molecules are going to want to kind of spread out, so it turns into liquid. Or gas, sorry, turns into gas. Turns into gas. Which is like sublimation. Yeah. It sublimes. Does that make sense? Does that answer the question?
Yeah.
As the pressure decreases. Yeah. Okay. And I think Oh, also the water phase diagram is different because again, we talked about how ice is less dense than water. So most of the solid lines are kind of this way, this one's this way. So water's different. You should know that. That's pretty much it. Good luck.
Wait, can you go back?
Clapping for you. Good God. Any other questions before we leave? You can leave if you want.
Back. It's not that hard. No, what if it isn't
What?
that hard?
You should know who one's on.
But
Okay, have a good night, guys. Good luck.